Jai Hind to all. This is Dr. Shivani Agrawal. I am the assistant professor in AKGEC in IT department. Today's my presentation topic is cache memory basics and cache mapping techniques. So we start the presentation now. So what is cache memory basically? Cache is a high speed memory that is used for synchronizing the data from the main memory to the CPU. So it is lie between the CPU and the main memory. So it defines the path between the CPU and the main memory for transferring the data between the processor and the main memory, because the speed mismatching problem is occur when we don't use the cache memory. So it used to reduce the average access time to access the data from the memory. This is the basis of the cache memory. Now we have a diagram that shows that cache in between the CPU and the main memory. This diagram depicts that the main memory transfer the data in the form of the block transfer, and the cache memory transfer to the data to the CPU in the form of the word transfer. So data is transferred in the form of words between the cache and the CPU, and data is transferred into the blocks between the main memory and the cache memory. So this is the basic diagram of the cache memory. Now, when the processor need to write or read a location in main memory, it first check for corresponding entry in the cache. If the processor find the location in the main memory, so data is okay. If the processor find that the memory location is in cache, so a cache hit is occurred. So that known as a cache hit. If the processor does not find the memory location in the cache, so it known as a cache miss. So basically there are two type of operation: cache miss or cache hit. So this is the hit ratio. Hit ratio performs like as hit divided by the total number of X's. Total number of X's means hit plus miss. So this is basically find to the hit ratio. So this is a very important ratio that we find the data in the cache. Actually what happens when we require some data, so first we find the data into the cache. If the data is not present in the cache, so that data known as the cache miss. If the data is present into the cache, so it known as the cache hit. When the data is absent in the cache, so how we find the data? So we take the data from the main memory to the cache memory like as a block transfer. So this is the basic concept of the cache memory, and this known as the cache performance by the hit ratio. Now move to the next slide. This is the diagrammatic representation of cache and the main memory. Basically this is the main memory representation. The representation of main and the cache memory both are same, but difference between the block transfer and the line of the cache. So this is the main memory diagram. There are two type of defined addresses: memory address and the word. Basically the memory divided into the number of words. These are the number of words, and each word address by the memory address. So this is the addressable form. It is 0, 1, 2, 3, 4, 5 in this particular diagram, but how we have to assign the addresses of the main memory words. So basically the concept known as, if we have the 8 words means 2 to the power equals n equals to 8. So what is the value of n? N depicts the address, how many addresses we have to required for define the number of words. So if we have the 8 words, that is 0 to 7. So how many bits are required for define the addresses? That is 3 bits. 2 × 3 equals to 8. So 3 bits are required for addressing the 8 words of the main memory. So this is the basic concept of the main memory. When we define the lines of the cache or the format of the cache, so the words are same, but the address defined by the tag bits, that defined as a tag bits. So the line defined is that Main memory consists of 2 to the power of n addressable words, each word having n bit unique address. This address is unique. Suppose 000 to 111. So each bit, each 3 bits are unique for corresponding a word. The line define that a unique address. The cache consists of m line. Each line consists of k number of words and a tag. Tag is what? The address. So that tag represent as an address in the cache memory. Now the mapping function. Why we require the mapping function? Basically, when the data is not present in the cache memory, so we find the data in the main memory and we have to copy that data from main to cache. So how we have to change the word from the cache to main or main to cache? So that require a mapping function. So an algorithm is needed for mapping main memory block to the cache line that required which block of main memory transfer to the cache line. So that defined by the mapping function. So there are the 3 type of mapping functions. First is direct mapping, second is associative mapping, third is set associative mapping. So first I explain the direct mapping. Direct mapping, the name depicts as direct means we have to directly transfer the data from the main memory to cache. So this is the very simplest technique. Each block of main memory into only one possible cache line. Actually, in the direct mapping, we have a scenario of assigning a memory block from main memory to the cache. This is a basic problem that we have to not changing the data as per your required. This block is old as, so this block we have to replace to the this cache memory. So this is the basically of the direct mapping concept, that assign each memory block to a specific line in the cache. How we have to define the specific line in the cache? That defined by that formula, that is I equal to j modulo m, where I represent the cache line number, which cache line that main memory block is transferred. So I depicts that I equals to cache line number, j is defined as main memory block number, and m defines as number of lines in the cache. How many lines in the cache, which line we have to transfer the data from the main to cache memory, that defined by j defines which memory block number we have to transfer. So basically it represents as I equal to j modulo m. For example, we take an example, if the value of m equal to 4, that means we have 4 lines in the cache, right? Now, and we have 8 blocks in main memory. So which block of main memory transfer to the which line of cache? So basically that start I equal to j, the value of j is 0. For example, we want to change the 0 block of main memory into the mod 4. So the value represented I equal to 0. That means block number of 0 from the main memory transfers to the cache line number 0. So this formula depicts which block number of main memory transfers to the which cache line number. If we want the main memory block number 3 transfers to the cache line number, so which cache line we have to define for transferring the data? So it is I equals to 3 mod 4. So the basically value is 3. That means we have to transfer the third block of the main memory transfer to the third line of the cache. So this is the basic scenario of the direct mapping. Now this is a diagram that shows main memory and cache memory tag and word scenario. So that defined as main memory divided into the tag and the word offset, and the cache memory defined as the tag and tag line. Basically tag divide into two parts, that is tag and the line offset. That tag define the basic address and this define the line offset. So this is the basic scenario of the cache memory. This diagram shows how we have to divide the tag into the tag or line offset in the cache memory. So this is the main memory. Main memory divided into number of words. Words represent the W0, W1, W2, W3, and this B0 to Bj represents the block number. This is the block number. This is block number. This is words. Main memory divided into number of words, and each block have some words. So that depends as the B0 to Bj, and this is the diagram of the cache memory. Cache divided into the number of words, and each number of words defined as a line. This is the line offset. So it is defined as L0 to L, I to M minus 1. This is tag, defines as address. This is S, this is W, W means word, S means set. So how we have to define S represent the addressable length basically. So this is the memory address that divided into three parts. Which time that divided into three parts? When we have to represent the address of the cache memory. So it defined the three parts, tag, line and words. When this particular memory address defined for the main memory address, so it is defined as simple tag and word offset. So line represent as R, W represent as word that I already explained, and S plus W that represent as the addressable length. S represent the addressable length. So S minus R represent the address of the main memory. Okay. So we have to compare that address. If compare the address is for what? First we have to check the data into the cache memory. If the data present in the cache memory, then it is okay. This is known as the cache hit. When data is not present in the cache memory, so we have to find that known as the cache hit when data is present. When the data is not present in the cache memory, so we have to tag that data from the main memory. We have to transfer the data from the main memory to the cache memory by using the formula of I equal to J mod M. So this is the basic concept of the direct mapping. It is very simple, it is inexpensive, and the disadvantage is there is a fixed cache location. This is the main disadvantage of the direct mapping, that the cache location is fixed. When we want to transfer the block from main memory to the cache line number, so that place is fixed. We don't change the place of the cache memory. So hit ratio is very low in this particular mapping because the location is fixed. So this is the advantage and disadvantage of direct mapping. Now we move on to the direct mapping questions. So basically, block of main memory, how we have to find the block of how many blocks are present in the main memory. So it is size of main memory divided by the block size. So we have to find the blocks of main memory. Line of cache memory, we have to find out size of cache memory divided by the block size. So we have to find the lines of cache memory. How we define the tag size, block in main memory divided by the line. Divided by the line in the cache memory. So this is the tag size. Index bits, line plus words, address bit length equals to S plus W, tag size length plus word length. So these are the basic formulas that we use for the direct mapping. Now this is the question. A digital computer has a memory size of 64 words. A cache memory is 16 words. Cache uses direct mapping technique with block size of 4 words. So find out how many blocks in main memory. So basically there are 64 words in main memory. So the address bits are 2 के बाद 6 equal to 64. So there are 6 bits are used for the memory address bit length. So this length is 6 bits, right? And main memory, cache memory block is 16 words. when the blocks are 16 or the lines are 16, so address is 2 k 4 equal to 16. This is 4 bits. So how many blocks are in main memory? So main memory block, how we have to identify the main memory block? So this is the formula. Blocks of main memory equals to the size of main memory divided by the block size. So we have size of main memory is 2 to the power 6. Blocks are 4, so it is 2 to the power 2, so it is 2 to the power 4. That means 16 blocks in main memory. How many lines in cache? Size of the cache memory 2 to the power 4, that is 16 divided by 2 to the power 2. So it is 2 to the power 2, that is 4 lines in cache. So this is the 2 A and B part is solved. Now, how many bits are there in tag, line and word? So we have divided the address into the 3 parts. This is tag, this is line, this is word. We have 4 words, so the bit of address bit of the words are 2, 2 to 2 equal to 4. And the lines we have, how many lines we have to calculate? It's 4 lines. When we have 4 lines, the address bit of the lines are 2 and total bits are 6, 6 minus 4, so address bit is 2. But we have a formula also for finding the tag size. So it is blocks of main memory, that is 2 to the power 4 divided by 2 to the power 2. So basically 2 to the power 2. So these is also represent the 2 bits as an address for the tag size. Now, find the address bit length. So address bit length is the S plus W, tag size length plus the word length. So it is 2 plus 8, that is 10. So this is the numerical that we have already solved in the for the direct mapping. So this is the basic solution of the of this particular numerical. Now we have to move with the associative mapping. So the problem of the direct mapping we want to resolve actually. So we have to move with 2 types of mapping techniques, that is associative and the set associative. So in this type of mapping, the associative memory is used to store the content and address of the memory word. But we want that, we don't want to fix the location. So we have a solution in the associative mapping that problem arise, that solve the problem arise in the direct mapping. So in this mapping, we don't restrict for transferring the location from the main memory and the cache memory. That location is not fixed. But there is also a problem. Problem is what? We have to move any place of one block of memories, place any one of the any one line of the cache memory. So this is the associative memory. So in this memory, we compare the data. Diagram is same with the direct mapping, but some changes are there. There is no formula that is I equal to j mod m. We don't want to fix a location, that this is the particular location that we have to transfer the data from the main to cache. We don't have a fixed location. There are the several locations. Which location we want to change the data, we can. So this is the main of the associative mapping. Now we take a question for the associative mapping. So we want to change the difference from the associative mapping and the direct mapping. So in this mapping, because the location is not fixed, now the formula is divided into not a 3 parts, that is the tag, line and words. In this particular mapping technique, tag and line in the same place, because we have no concept of the line offset. So we place we combine that those particular tag and line into the single space. So if we have a memory size is 256 bytes or words and the cache is 16 words, so find, and the block size is 4 words, so find out how many bits are there in tag, line and words. So basically 256 words, that is 2 to the power 8, 16 words, that is 2 to the power 4. So find out the blocks, main memory blocks, that is 2 to the power 8 divided by 2 to the power 2, that is 2 to the power 6. Number of blocks, number of lines are 4 divided by 2 to the power 2, that is 2 to the power 2. These are the lines in the cache. So the address bits are 8, total address bits are 8 in the memory address fields, and the words bits are 2 bits, and tag plus line. So this is basically obviously 8 minus 2, that is 6. So this is very simple as compared to the direct mapping, but there is also a problem that we have to transfer the data from any location, but we don't want that location is transferred, so we have to change the location accordingly. So this is the basic numerical of the associative mapping. Now the set associative mapping, this is a combination, this is a advantage of direct, advantage of associative. We have to combine those advantages in a single way, so that mapping technique known as the hybrid mapping. This form of mapping is an enhanced form of direct mapping, because we want, basically remove all the drawbacks of the direct mapping. So this is known as the set associative mapping. The name depicts as we have to divide the locations into the number of sets. Number of sets means we have to identify how many blocks of main memory take place, how many blocks of main memory take place in the block of the cache per set, not per line. In the right we use a line, but in this we use a set, and that is K-way set associative mapping. Basically, K-way means we have a different number of ways to represent the set associative mapping. Either it is one way, either it is 2-way, 3-way, 4-way. So these sets are changed accordingly. Set associative mapping allow each word that present in the cache have 2 or more words in the main memory. So same index we have to change a number of locations of the cache line into the main memory. So this is the advantage of the set associative mapping. Now these are the formulas of the set associative, that is M equal to V multiplied by K, I equal to J mod V. J mod V, where what it represents, where I is the cache set number, same as I equal to J mod M, but V represent the number of set. How many sets are there? We represent that. So in this, the tag divided into 2 parts, tag and set of set. Okay. The major formula that we have to use in that is set number of set equal to block of cache memory divided by the K-way set associative mapping. So we take an example for that. This is the basic diagram. If we have to change the one block, we have to change the number of sets. In one place of the main memory, one line of the cache memory have the number of sets. So a data computer has a memory size is 128K bytes or words. A cache memory size is 2048. Cache uses set mapping technique with block of 4 words, and each word consists of 32 bits. So find out how many blocks in main memory. So obviously first we have to find the address bit size from the main memory size. So it is 128K. It is 128K, that is 2 to the power 17, and block size is 2 to the power 2, that is 4. So 2 to the power 2. So it is blocks in main memory is 2 to the power 15. Lines in cache memory is 2 to the power 11 divided by 2 to the power 2, that is 2 to the power 9. So 9 represent the lines or address in the cache memory, and this 15 represent the address bit length of the main memory. Find out how many sets are there. So it is basically block of cache memory divided by the number of sets. So it is 2-way set associative, so it is 2 basically. So the number of sets are 2 to the power 8, right? So this is the address bit length. This is 2 to the power 17 of the memory address length. This length divided into 3 parts, text, set and words. Words are 2 bits and the set are 8 bits that we have to define and by the formula, that is 2 to the power 8. So 8 bits are represent the set bits. We have to get 8 sets. So this is the 8 bit represent the address of the set. And how many tags are represented? That is 17 minus 10. That is 7 bits are used for the tag. So this is the basic question of the set associative mapping. Thank you.